Hello students, this is Assistant Professor Samiya, Department of Electronics and Communication Engineering, Oriental Institute of Science and Technology, Bhopal. Our topic for today is SR flip-flop. Firstly, to understand what flip-flops are, we need to understand what are sequential circuits. So, sequential circuits, as we can see in the diagram, here is a combinational circuits which we all know are adder and subtractor. Combinational circuits are those circuits in which the output depends only on the present value of the input. Okay. Combination circuits, the output depends only on the present value of the input. But in sequential circuits, the output depends on the present input as well as the previous values of the input. Thus, I'll make it clear that the output depends on the present input as well as on the previous input. Thus, to store the previous input, we need a memory element. So, in sequential circuits, we are here having a feedback system from which we can get the previous input. So, now this output is dependent on the present input and its previous inputs also. So, to store that the previous values, we have used a memory element over here. Okay. Now, sequential circuits are classified in two types. They may be asynchronous, they may be synchronous. Now, first we'll discuss about the asynchronous sequential circuits. Here we can see that in asynchronous sequential circuit, here output is defined and here we are having input levels. Now, these inputs can either be a present input or previous input. Okay, it can be a present or previous or both. Okay, so here what happens is, as soon as you give the input, you will suddenly get an output. You will get a result instantly. So there is no need of clock pulse for synchronization. So as compared to other circuits, these are comparatively faster, as we are not using any kind of clock pulse over here. We just give an input and we instantly get an output. These are asynchronous sequential circuit. Why we are using a term asynchronous? Because we haven't used any external input for synchronization. No synchronization is done over here. So these are asynchronous sequential circuit whose output depends on the values of various inputs. Okay, without any clock pulse. Now come to synchronous sequential circuit. Here we can see the diagram of synchronous sequential circuit. What's happening is, here we are having output pulses of levels and here the various input levels. And these inputs can again be a present input and previous inputs. Okay, but here we have used an external input which is a clock pulse. Why we have used this clock pulse? We have used this clock pulse to achieve synchronization. Like, depending on the circuitry, whether this clock pulse is high or low, the output will be generated. Suppose this is a logic high circuit, active high circuit, okay? So then whenever the clock pulse is low, then only we'll go to the values of the input and the output will be generated accordingly. So every time for generating an output, we have to wait for a clock pulse. In this way, our output is synchronized with the help of this clock pulse. Okay, so as compared to synchronous sequential circuits which we have discussed, here there is no clock pulse, but and as there is no clock pulse, there is no synchronization. But in synchronous sequential circuits, we are having a clock pulse, and our output is synchronized with the help of this clock pulse. So here synchronization is achieved, but these are comparatively slow than asynchronous sequential circuits, as we have to wait for a clock pulse every time in synchronous sequential circuits to achieve synchronization. Okay, now we'll come to the SR flip-flop. Now what actually SR flip-flop is? SR flip-flop is a sequential synchronous circuit. Sequential means the output depends on the present value of the input as well as on the previous values of input. And synchronous here means we have used a clock pulse. So SR flip-flop is basically what? It is a Sequential synchronous circuit. What it functions like? It's a memory device used to store one bit of binary information. So, it's a synchronous sequential circuit and is used to store only a single bit of information. Only a single bit at a time can be stored in any flip-flop. Here we are discussing SR flip-flop. As it can be seen, here we are having a block diagram of SR flip-flop. This is S pin, input pin. This is an reset input. Okay, here the output is generated, which is denoted by Q, and the Q bar is the inverted output, right? Q bar is the complement of Q. And here we have use of clock pulse. Remember, we have use of clock pulse to achieve synchronization, as it is a sequential synchronous circuit. Okay, I repeat, this is input S, set input, this is reset pin, this is output, and this is the inverted output. This is the basic block diagram of the SR flip-flop. Now we will discuss about the logic diagram of SR flip-flop. Now here is the logic diagram of SR flip-flop. As it is very clear, here we have used two NOR gates. As NOR is a universal gate, so we prefer NOR or NAND gates. Here we have used two NOR gates. As shown in the diagram, the output of the first NOR gate goes to the input of the second NOR gate. And similarly, the output of the second NOR gate becomes the input of the first NOR gate. Okay. Now, here we have to give a clock pulse. We can't give the inputs directly. So we have used AND gates to generate clock pulse. What we are doing is, with the reset input, we are giving a clock, and with the set input, obviously, we are giving a clock. So for giving a clock, we have used two NAND gates over here. Why we have used AND gate? Sorry, AND gate. Why we have used AND gate? We have used AND gate because whenever the one of the input is low, the output of the AND gate will automatically be low. So if it is an active high circuit and if the clock pulse is at logic 0, okay, if the clock pulse is at logic 0, it doesn't matter whatever be the values of R and S. If the clock pulse is 0, here what will be generated? 0, and here also 0. So 0 will go inside this NOR and 0 will go inside this NOR. So here, this is the reason why we will use AND gate for giving clock pulse. Okay, I repeat, we have used NOR gates over here, which are crisscross connected. Output of first NOR gate is acting as an input to the second NOR gate, and output of the second NOR gate is acting as an input to the first NOR gate. To give one clock, we have used AND gate over here with reset and set inputs. Okay, now we understand the functioning of this flip-flop. To understand its functioning, we have to first be well prepared with the functioning of the NOR gate. As we all know what NOR does, it is a complement of the OR gate, and we have to keep in mind the function of the NOR gate to understand this whole logic. Now, I'll explain you the functioning of the RS flip-flop with the help of a waveform. Remember, we are considering here that our circuit is active high circuit. It means that whenever the clock pulse will be high, the output will be generated, and whenever the clock pulse is low, the circuit will not function accordingly. Now here we will come to the waveform. As you can see, this is a waveform of RS flip-flop. Here this is a clock pulse. This is going low, this is high, again low and high. This is an preset input. This is a set input, and this will be a generated output. Now, pay attention. Here the clock pulse is low. Suppose earlier the circuit's state means this Q was 0. Earlier it was 0. Suddenly the clock pulse is 0. Okay, we'll start with the initial condition that this output was previously 0. This is 0 previously. So if the clock pulse is low, our circuit is active high circuit, but the clock pulse is low. The clock pulse is low, so it doesn't matter what values you have given on R and S. The output will not change at all. Suppose we have assumed here that the previously it was in zero state. So now as the clock pulse is low, there will be no reaction and the circuit will be on its previous state. It was 0, so now after low clock pulse it is 0. It doesn't matter what are the values of R and S. Now come to the next, which is important. Here the clock pulse moves from low to high. In this portion, the clock pulse is high. Here the clock pulse is high. So now what happens when the clock pulse is high? We have to check the value of R and the value of S. As the clock pulse is high, we will check the value of R, which is low, that is 0, R is 0, and the set, yani S input is high, R is 0, S is high, and now we will see what happens. Clock pulse is high, R is 0, clock pulse is high, that is this is 1, this is 0, here we will get what? 0. This is S is 1 and clock pulse is 1, we will get what here? 1. Previous state here, according to our waveform, previous state was 0. This was the previous state. Okay. So this is the previous state. Here we are getting 1. Here we are getting 0. Here 1. And this is 0. So what happens is this 0 will go inside this and this 1 will go inside this. On 0 and 1, NOR gate will generate 0. This 0 will go inside this as the output of the second flip-flop is connected to the input of the first flip-flop. So the 0 will come here and here, from here what we were getting, here we were having 0. So 0 and 0, the output will be 1 for NOR gate. So it is clear that earlier this output was 0, but now when we have given R is equal to 0 and S is 1 and the clock was high, so we are getting what over here? 1. So according to the waveform, when clock is high and reset input is low and S input is high, the output will always be high. For the next move, here the clock pulse is low. Doesn't matter what are the values of R and S, if the clock pulse goes low, the circuit will remain in its previous state. Earlier we have set the circuit to 1, but now for the next cycle, that is this portion, our circuit will show no changes because 1 will continue to be 1 until the next positive part. Okay, so here now we have got a high, clock pulse high. Here we are having a high clock pulse. Again we will check the values of R. Now R is 1 and S is 0. So we'll move to this circuit. Clock pulse is high, R is 1, clock pulse is high, that is 1 will be generated here and S will be generated here. Earlier its circuit's state was, circuit's previous state was 1. So R is 1, clock is 1, so 1 will be generated here. S is 0 and clock is 1, so 0 will be generated here. Earlier Qt was what? Qt was 1. Now 1 will go inside this and depending on the values of R and S and high clock pulse, as R is 1, the next output, that is the next state, will be 0. As it can be seen in the diagram. Here it is a positive half cycle. Okay. Now R is 1, S is 0. Depending on the form of this logical diagram, we come to the conclusion that this state will become 0. And obviously this is its complement, it will be 1. Again move to this part. Now we are in a state 0. We have seen a low clock pulse. Doesn't matter what is R, doesn't matter what is S. What the circuit will do? Circuit will not changes its state. So circuit was earlier reset to 0. Now it will continue to be at 0 unless it will find another positive part. Okay. Now this is again a high clock pulse. For high clock pulse, we have to check the values of R. Here the R is 1 and S is what? 0. When R is 1 and S is 0, the circuit will be reset. It is at 0. It will continue to be at 0 unless it will find another positive clock pulse. Then it will decide what it has to do depending on the values of R and S. So after discussing this whole procedure, we come to the conclusion that whenever the clock pulse is high, this procedure will only be considered whenever the clock pulse is high. Whenever the clock pulse is high, S is 0 and R is 0. That is, both the inputs are 0. S is 0 and R is 0. The output of both the AND gates will be 0. 0 will be gone here, 0 will be going here. So it doesn't matter whatever be the earlier stage of the circuit, whether it can be earlier, suppose earlier 1 was stored here. Now I have given R is 0 and S is 0. Now, according to the function of the NOR gate, there will be no change in the next state. 1 was here, here we have given 0, here we have given 0. Now the circuit will remain in its previous state, that is, the next output will always be 1 itself. Okay? If circuit was at 0 state, suppose 0 was stored here, while giving R is 0 and S is 0, the circuit will not change its state, and here we'll get the next output as 0. Okay, so we have seen that when S is 0 and R is 0, there is no change in the circuit's state. The circuit state remained unchanged. So what we are having here, S is 0, R is 0, the output Q and, okay, which is showing the no change in the state, and this is Q and complement. When set input is 0 and reset input is 1, as we have discussed for this part, when S input is 0 and R input is 1 and clock is high, the circuit will reset to 0. So, whenever the R input is high and the clock is high, the circuit next state will always be 0. Doesn't matter what was the previous state. Similarly, when the set input is high and the reset input is 0, circuit's next state will always be 1. Doesn't matter whatever is the previous state. Okay, but the important thing to notice over here is when both the inputs, when S is 1 and R is also 1, what happens in this state when S is 1 and R is 1? What happens is, let's talk to this about the circuit. We'll understand this better by looking at this diagram. When clock pulse is high and R is 1 and S is 1, both the inputs are 1. Suppose 0 was stored here. Okay. Now here we are giving 1. Here we are giving 1. 0 was stored here. According to 0, and here we are having 1. 0 and 1. The QT complement will be 0. Now this 0 will go here. Here we are having 1. Again for 0 and 1, QT as the NOR gate functions will be 1. Important thing to note over here is when Qt is 1, how it is possible that Qt bar is also 1? It is not at all possible because a complement and a normal cannot be same at a time. It is impossible. So this condition for RS flip-flop or SR flip-flop is known as forbidden condition, as this condition is undefined for SR flip-flop. Which condition is undefined? For NOR-based SR flip-flop, the condition when S is 1 and R is 1 is undefined, or it is called forbidden state. Students, here we have used a NOR gate for building SR flip-flop. We can also use a NAND gate, but the difference will be in the functioning. It will be almost same, but depending on the functioning of the NAND gate, the truth table will slightly be different. So, here we have discussed and we got in the conclusion that when S is 1 and R is 1, the circuit states is not defined at all. This is the major drawback of the SR flip-flop. This is called the forbidden state, and to remove this, we have designed other flip-flops. Okay, we realize the need to develop other flip-flops It can be a D flip-flop, it can be a J or T. In my upcoming videos, I'll be discussing about how we can remove this forbidden condition and what other flip-flops can overcome this condition. Hope I'm clear with my lecture. Again, I'm repeating, this was the truth table of as a flip-flop. This logical diagram was made using NOR gate. You can also implement this diagram using NAND gate. Okay, this is the basic block diagram. Hope we have discussed as a flip-flop quite well. In my upcoming videos, we will be discussing next flip-flops. Till then, all the best. Stay connected. Thank you.